Hi everyone, how are we doing today? So today we'll talk about approximate integration, or numerical integration as it's also known. But first, let's remember what we did last time, and that is methods of integration. At this point, I'd like to ask you to recall what are the main methods of integration that you're aware of, that you can recall, at least based on the way that your integrand, that is the function under the integral sign, looks like. So maybe pause the video for a second and recall all the main methods of integration based on the shape of the function. Is it a product of two things? Is it not? Do the two things look alike or do they not? This kind of thing. All right, so let us now discuss the approximate integration. And today we will first discuss why to do that. Why do we do it? So first point is on the agenda is why. Then after we motivate our idea to go for approximate integration rather than exact, then we'll discuss how to do it. And there will be four major methods discussed today, but to the best method we'll probably only get to in class. So, but still these four major methods will provide the basis of that one extra method that we will develop in class. And actually that will be the method that is currently in use in all the applications, pretty much in all the applications, starting with your calculator and ending with NASA guiding the spaceships in the universe. And then a more subtle question is how accurate this approximation method will be. So which will be the best? So accuracy. Today we'll just pose the question, but in all earnestness we'll discuss that in class. Okay, that's what we're going to do today. The vocabulary. Our vocab for today, new words will be first maybe start with some old ones that you may recall, but from Calc 1, but maybe forgotten. Most important is Riemann sums, and of course Riemann integral. And then from that we'll get to our approximating methods, which we'll simply call left or right hand, or simply left or right rule, or approximation. Then we'll also talk about midpoint rule. We'll talk about trapezoid rule. And eventually we'll develop Simpson's rule. Some people forget it on the exam, so instead of the formula for the Simpson's rule, they just draw me a face of Simpson from the cartoon, but they'll get some partial credit, sure. And then we'll talk about the idea of the error, right? Accuracy means that we have to understand the error. So how do we define this term, error of approximation? So that's our plan for today. Most of it, of course, will happen in class. But let's get started. So why? Let's get started with why. Well, why do we do it? Sometimes it's all about the cost. Cost of what? Not cost in dollars, but cost of computation, cost of computational resources. How long does it take? Maybe it's cost in time, maybe it's cost in dollars, the equipment. But frequently, even if you have a perfectly integrable function, the function that you can integrate, you can find the antiderivative in elementary functions. And we discussed last time, it's not always possible. But even in these cases, you may want to do approximate integration just because it takes so long to get the exact answers. Why the time may be of importance? Let's say if you are running a program which predicts certain stock price. Let's say you're working for a quant on Wall Street and you want to beat the competition. Then to be absolutely precise is not as important as to be a little bit faster. And you can use some of these advanced methods like Simpson's rule to get your approximate integral before they get the exact one and beat them to the deal. Sometimes indeed, if it's a real-time situation, like when you're developing, again, talking about the spaceship trajectories, corrections, if something happens, then again, you want to be fast. So cost, computational cost, we mean. Other times, as we said before, so even if antiderivative can be expressed in elementary functions, can be obtained in elementary functions. Other times, you are dealing with a function which cannot be explicitly integrated in elementary functions. Antiderivatives, so for instance, something like this, e.g. e minus x squared dx, very frequent integral in statistics. So can't be obtained exactly in elementary functions. And last time, maybe the function that you are trying to integrate doesn't even exist as a formula. So, or maybe exists abstractly, where you're trying to take this integral, let's say from a to b, but f of x is only given by numerical data. So you have a bunch of data points rather than the formula. Okay, so why now is cleared. Hopefully you're motivated enough to do it. Then how do we do it? Okay, so to understand how, let's recall the definition of Riemann integral. Good idea here is to pause the video and can you define from Calc 1, it happened late in Calc 1, to understand our approach, at least, recall the definition of Riemann integral from Calc 1. So pause it for a second and write down what this means by definition. Now the hint, it happened at the end of Calc 1, and it will involve two major ingredients. Will involve a limit, of course, everything in calculus has to include the concept of a limit, pretty much, and subdivision of or partition. Sometimes we say subdivision, sometimes we say partition. We'll use it loosely. Sometimes subdivision refers to a part, a small part of this partition, of the interval AB. Okay, can you recall it? Pause the video and try to remember itself. Quizzing is very important part of learning. Hopefully, if you came back with something, let's talk about the answer. If there's a question, there must be an answer. Of course, it's defined as the limit of our first term. That was the Riemann sums. So Riemann integral, not surprisingly, will be defined as the limit of the Riemann sums. So let's define it then. We will say that integral a to b f of x dx. We assume that f is continuous here, continuous function, will be given as the limit as n goes to infinity, and n is the number of subdivisions in our partition. So what are we talking about? We are talking about partitioning our interval, our segment AB, into x naught, which is equal to a x1, which is a plus delta x, x2, which is a plus 2 delta x, and so on and so forth, where x sub I is a plus I delta, I times delta x, until xn is equal to b. So that is our partition where this is a partition of AB segment. So given this partition, we will write the limit of the Riemann sum. We will take sum from 1 to n of what? We pick the value of the function anywhere inside the subdivision. So we can say it's a partition of AB into intervals from xi minus 1 until xi. That would be interval number I. So for each such interval, we'll take the value of f somewhere inside that subdivision times delta x, where by delta x, we mean the difference, b minus a divided n times. So we will take, f of x sub I superstar. So that is not one of xi's, but xi superstar is some point inside xi minus 1 xi, inside that subdivision. And the claim is that if we pick these x superstars anywhere inside our subdivisions, in the limit, if this limit exists, then it does not depend on the choices we make of this points, superstar points, to evaluate our f at these points inside our subdivisions. So maybe before we move on, a quick graphic of what we are doing here is just take the graph of the function, let's say from a to b, divide it into n subdivisions, and on the subdivision number I, which lasts from x sub I minus 1 until xi, ith subdivision, we will pick some value of x inside, and we'll call it xi superstar. Then we will evaluate the value of f at this point, let's say, and we will make this product fxi times delta x. In other words, that will create the this product will create the area of the rectangle. Oops. We'll create the value of this rectangle, and we will sum up these values. And this will be an approximation. So we'll sum up all these values for each subdivision. And that will be an approximation to the whole area. And it becomes more and more precise the larger the n appears. And in the limit, we will get the integral, which we interpret as the area under the function if f is positive. So that's area is just an interpretation of the integral. Okay, good. So we review the concept of Riemann integral, and this part, of course, is the famous Riemann sum. So based on this definition of exact integral, we'll understand how to approximate in more or less accurate ways. So let's start with all of these methods of approximating the integral are related to the choice that we make of this small xi superstar inside the interval. So the choice that we make inside that interval of this x superstar. Okay. So let's write it down. So all methods, basically almost all simple methods, all primitive methods of approximation are related, are based on a certain choice of those points inside each subdivision, inside subdivision number I, xi minus 1, xi. So for instance, we can choose all of them to lie on the left on the left-hand point of each subdivision. Then we will get the left-hand rule. So e.g., choose all of them to be on the left. And that means that xi superstar is just equal to xi minus 1. Then we will say that our integral f of x dx from a to b is approximately equal to the Riemann sum I goes from 1 to n, where all the choices are xi minus 1 del x. So if we roll out this sigma notation, what it really means is we are taking f of x naught delta x plus delta x can be taken outside plus f of x1 plus dot dot dot, and where we're stopping at x n minus 1. That's the last selection, and that is what we will call as the left-hand rule with n subdivisions. So that is, by definition, that's how we define the left-hand rule with n subdivisions. To summarize, L sub n will be equal to, sometimes we like to put delta x in front, f of x naught plus f of x1 plus dot 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 f of x n minus 1. Similarly, right-hand rule, or just right rule with n subdivisions. Then we will have delta x. Now we will start in the rightmost point of the first interval. The first interval is from x0 to x1, so we'll end up with f of x1 plus dot 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 plus fxn minus 1 plus the very last one will be f of xn. Another interesting choice would be to choose all of the points to be the midpoints. So this is the left rule, this is the right rule. How about the midpoint rule? We will call it m sub n. So that's when all the points are exactly in the middle, so of each subinterval. So in that case, it's neither x0 or x1. We will call it for the first interval x1 bar. That will be actually x0 plus x1 over 2. So all the points are taken to be the midpoint of each interval, f of x2 bar plus f of xn bar. How does it look on the picture? So for instance, if we are looking at a function, let's say same exact function as I have drawn before, and we subdivided the interval from a to b into, let's say, four subdivisions. 2, 4, 4 subdivisions each. Same exact function. Never mind, my drawing may be not perfectly identical, but if we now draw the left-hand rule, then we have to draw height of all rectangles from the leftmost point. So that's our first rectangle, second, third, and fourth. For the right-hand rule, we have to go from the right side. This, that, and that, and that. So you see that they're not identical. Okay. So that's the right-hand rule. And what about the midpoint rule? So here we have to go in the middle. So if this is A, this is B, and I have to go in the middle of each interval. This is my x bar 1, x bar 2, x bar 3, and so on. And I have to find the height at that point, at this point, at this point, and at this point. And then this will be my approximation to the area. So they are not the same, as you can clearly see, right? Which do you think will be more accurate? Think about it. We'll come back to this question soon enough. Then comes the more interesting rule, more sophisticated rule. So next more sophisticated rule is trapezoid rule. So by trapezoid rule, we will just mean the average between the left and right hands rule. So trapezoid. We will say T sub n, that would be just Ln plus Rn over 2, just average. Left and right hand rules. Okay, very good. We can easily write the formula, right? So we can say if we do the average here, so pay attention to Ln, let's redo the the whole formula f of x naught plus f of x1 plus dot 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 f of x and minus 1 and right hand rule. So all we have to do is to add them and divide by 2. So right hand rule is of course delta x, f of x1 plus f of x and minus 1, but we also have here f of xn, which we didn't in the left hand rule. So in the sum, if we add it first, Ln plus Rn will be delta x, of course, is the common factor. F of x naught will appear once, but we'll have 2 f of x1 plus twice f of x2. Similarly, through f of x and minus 1. And then only one f of xn. Now, finally, if we have to average, then we'll take ln plus rn divided by 2. Then that's what we'll get. Delta x over 2 f of x naught plus twice that plus until xn minus 1 plus finally f of xn. And that's our formula for the trapezoid rule. Trapezoid. So remember all of these formulas. If you forgot the trapezoid rule, you can just remember that that's the average and derive it. Good. So these are the important formulas. This one and this three. But now my question for you is which part of the trapezoid rule suggests that there is a trapezoid? So where's the trapezoid? In other words, question: where's the trapezoid in the trapezoid rule? In the TN rule. Pause for a second. The hint is, of course, you have to draw a sketch, and after you come back, hopefully you have drawn something like this. I'll just draw one single subdivision. So this is my f of x, and I have xi minus 1, so that's my ith subdivision xi, and here I may have the left-hand rule gives me something like this, the right-hand rule gives me something like that, but what if I want the average? One way to average geometrically is just to take this middle line, this diagonal in this rectangle, so that as a result I will get the trapezoid right here. Okay, all right, maybe is that to redo the diagonal. So that's based on this diagonal. I don't like this highlighting, so let me try again. A little bit more accurate work. So I have to be careful not to highlight too much. I just mean this trapezoid. So of course, I'm missing out this part. And that's why it's an approximation, not the exact value of the integral. So based on this picture, what is the area of this trapezoid? Well, the area of the trapezoid is just the area is just 1/2 between the two bases. What are the two bases? So this side is f of xi minus 1, and that side is f of xi. So that would be the average between the two bases, f xi minus 1 plus f of xi over 2 times the height. The height, of course, is delta x. Right, you're looking at the trapezoid sideways. Usually your bases are like this, and you're looking at the trapezoid like that in high school geometry. So that's your high school geometry trapezoid. But this is the trapezoid that we're looking at in calculus. So based on this area of the single trapezoid, the entire area, if you sum up all the trapezoids, then of course I'll leave it to you to sum them all up. You should get exactly the formula that we've gotten. So in other words, the total area would be, start with the very first trapezoid, f of x naught plus f of x1 over 2 times delta x plus f of next one will be f of x1 plus f of x2 over 2 times delta x plus so on and so forth. So if you finish the calculation, you will see that that's exactly the same as ln plus rn over 2. So question for you is to finish that calculation and show that the total area of all trapezoids is indeed equal to ln plus rn over 2. So just massage this sum and show that that's equal. But why? That is up to you. Okay, so we've gone through the 4 simple methods which I promised. And now let's do an example. Next time we'll talk about Simpson's rule. So next, or in class, I should say. All right. So class will introduce one more method, Simpson's rule. And that will rely on parabolas rather than the straight lines. So here, all that we've done relies on straight line images. But maybe I can ask you right now, among the 4 methods, which is your favorite as far as accuracy? Which one do you think is more accurate? Among the 4 above, that is left, right, midpoint, and trapezoid, which one is your favorite? In other words, most accurate. We'll come back to it a little bit at the end and discuss it in detail in class. So now the example that I promised. Let's take a look at a typical calculation that you'll have to do on a test or an exam or whenever you are doing the approximation. And that's what actually happens in the guts of your calculator when you ask it to do numerical integration. So let's find at least a setup, find setup. Maybe I'll find one exactly. Finish the calculation and set up the other T4 and M4 for this integral. We'll do integral from 1 to 2 of 1 over x dx. What's the point, you may ask, of doing the approximate integration for an integral which we can't find exactly? Well, the reason to do that is exactly that we can cheat and find the integral exactly, so it allows us to evaluate each of the methods that we want for accuracy. But first, let's do the setup and the calculation. So what are we doing graphically, first of all? How does 1 over x looks like between 1 and 2? At 1, it is equal to 1. At 2, it is 1/2. And before it's going up to infinity. Oh, let's try again here. Okay, so this is my 1 over x curve, and I'm trying to approximate the area between 1 and 2. So even though I'm trying hard to approximate this area, My choices are two methods. So for T4 trapezoid, what do I have to do? I have to divide it into 4 pieces, but this is 3/2, this is 5/4, this is 7/4. And on each piece, I will have to draw my trapezoid. Trapezoid, 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 trapezoid. And these 4 areas will give me one approximation. For the midpoint, I would have to go to the midpoint of each interval and evaluate the function there and do the calculation, get the result. That would be this jagged staircase will be my approximation. All right, let's start with the trapezoid, so T4. Then we'll do setup for M4. Maybe I'll leave you to finish the M4. Okay, so for T4, what is the formula? Do you remember? We averaged left and right, so of course we got del x over 2. And then write the general formula first. That's the most effective way to avoid mistakes. F of x naught plus twice f of x1 plus twice f of x2 plus twice f of x3. How many points do we have? If we divide it into 4 pieces, let's do it again here explicitly from 1 to 2. So we subdivide it into 4 pieces, 3/2, 5/4, 7/4. Then we have 5 points, right? So the last one appears by itself without any coefficient. The middle points appear with coefficients too. Now we can plug things in, and we see that what is delta x? Delta x is 2 minus 1. Even if we start with b minus a, maybe that's better. B minus a divided by n. B is 2, a is 1. Divide by 4. So we have 1/4. And that is 1/4 that we plug in and has to be divided by 2, right? So what do we have inside? F of x naught, which is 1 plus twice f of the next point, 5/4, twice f of 3/2, plus twice f of 7/4, plus f of the last point, f of 2. So if we continue here, then we will have outside 1/8, and inside now let's find the values of all this. So every time, since f is 1 over x, then we have to do the reciprocal. 1 over 1 plus twice 1 over 5/4 is 4/5, plus twice 2/3, plus twice 4/7, plus twice 1/2. So we'll have something like that. 1/8, 1 plus 8/5, plus 4/3, plus 8/7, plus 1. So let's finish the calculation. I have the calculator nearby, but unless it says find approximately, then usually you expect to find the exact value. So you have 2. What's the common denominator between 5 and 3 and 7? Looks like they're all primes, right? Not divisible by anything else. So 7 times 15 is 105, right? So we have 105. So 8 times 21 plus 4 times 35 plus 8 times 15. Makes sense? Check it out. So we'll get 1/8. So if the common denominator is 105, then here we'll have 210 instead of 2. And here we'll have 168 plus 140 plus 120. Long story short is we'll get 260 plus 210 will give us 470 plus 168. Plus 170 will give us 5 plus 140. 640 minus 2, 638. So it looks like 1/8 times 638 divided by 105. So remember that on the bottom you have, what did you have? 5 and 3 and 7. So 7 times 5 times 3. So what do you have there in 638? 638 is definitely divisible by 2, so you'll get 319, right? Times 2, and you can cancel that and get 4 here. Is it divisible by 3? No. By 5? No. By 7? Good question. Looks like it's divisible by 7. So 280, 40 times, and from 280 we have 39, not 49. Maybe not. Maybe not divisible by 7. Maybe not divisible by 7, so if we want exact answer, we'll leave it like that. 319 divided by 420, but approximately we will get, plug things into my calculator, 319 divided by 420 will give me 0.76, let's say, and that's our approximation for the trapezoid rule. Good. So what about the midpoint rule? For the midpoint rule, we'll have to find all the midpoints. So what is this midpoint? Between 1 and how many eighths? And 10 eighths. So this will be 9 eighths. Then this midpoint is between 10 eighths and how many eighths? 12. So this will be 11 eighths. Or every time you can just add 1/4 or 2 eighths. 13 eighths and 15 eighths. So for at least the setup will look like this for the midpoint rule. For subdivisions, we would have to write here delta x. Of course, the general formula is what you want to start with. F of x1 bar plus f of x2 bar, so on. And now plug in those midpoints. So del x we already figured out was 1/4. That's what we'll put in, times. We want to find the f of 9 eighths. Means we'll take reciprocal in the next step. F of 11 eighths, f of 13 eighths, and f of 15 eighths. So this will be equal to 1/4 times 8 ninths plus 8 elevenths plus 8 thirteenths plus 8 fifteenths. So if I take 8 outside, I'll gain 2, and then I'll be left with 1/9 plus 1/11 plus 1/13 plus 1/15, all except for 15 are prime numbers, but I'll leave that to you to finish. Okay, and that's the promised example. Okay, so now finally work through this yourself, maybe if there are still questions, or bring them to class. Finally, let's talk about our last topic on the agenda, is how well our approximations are. So we want to discuss errors of approximation. Okay, errors. All right, so what do we mean by the error? That's amount that is missing, that we miss the exact answer by. In other words, so the idea will come from exact answer being understood as the approximation. That could be either of our rules that we've introduced so far, plus the error. So for instance, if our exact integral f of x dx from a to b could be approximately expressed as, let's say, trapezoid rule with n subdivisions, then instead of writing this, we will write it's exactly equal to Tn plus the error, we'll say E of t. We could write Tn here, but just for to keep the notation simple, we'll just keep it as E sub t. T refers to the method that this error was obtained from. So from here we can define the error. So here's our definition of the error is E of any method. Let's say T will be the difference between the exact value and the result that the method gave us, minus T sub n. And we'll look at errors, and similarly for others. Similarly for other methods, we'll look at all the errors of all the methods that we introduced so far, as well as the Simpson's method, which we'll introduce in class, and see which one is more precise. So we'll see which errors are smaller. We'll even come up with some formulas to estimate those errors. So that's the goal for next time. Goal for in class meeting, of course. Goal is estimate the errors for all the methods, ET, EM, EL, ER, as well as error for the Simpson method. So this will stand for Simpsons. Question for you. Maybe you can guess it right now. Can you rank the methods in order of accuracy? Or at least the ones that we've seen today, of course. You can guess. You can also try and guess how is the Simpsons method gonna fare. So rank them in order of accuracy and tell me your guesses, or look them up in Wikipedia if you're stuck or somewhere on the internet, and try to understand why one is more accurate than the other. So we'll see which methods rank best, and also we'll try and answer the question why. That's of course the most important one. All right, that's it for now, but we'll do more in class. I'll see you then.